All right, in this section we're going to do calculus with parametric curves. So let's suppose we have a set of parametric equations. And let's just draw a graph. Let's say we have this curve and it's just minding its own curvely business. There we are. And we have a point on this curve. Now, suppose we're interested in the slope right here of the tangent line. So even though we're working with parametric curves, the slope is still the rate of change of y with respect to the rate of change of x, right? It's still going to be dy dx because it's still rise over run. So we're really looking for dy dx, but how could we find dy dx when this curve is defined in terms of parametric equations? Well, we know you can take the derivative of any variable with respect to any other variable simply by using the chain rule. So let's see how that works here. By the chain rule, dy dt would simply be dy dx multiplied by dx dt. Okay, so solving for dy dx would give us dy dt divided by dx dt. And there it is. That's actually how we're going to be finding dy dx, simply by finding both dy dt and dx dt, and then writing them as dy dt over dx dt. And voila, there we are. This is going to give us a nice equation in terms of t. So we'll have the derivative of y with respect to x as a function in terms of t. So that's great because that's kind of the system we're working in, right? We want to have t as our input, that's usually time, and it's like asking the question, what's the slope of this curve at a specific t value? Great. This, of course, requires that dx dt is not equal to 0. So yeah, before we go and do actual examples, let's take one more level of derivative here. Let's go to the second derivative, because we know that's going to give us information about the concavity of the curve at various t values, and that's not much harder to get. So the second derivative of y with respect to x, that of course simply means the derivative with respect to x of dy dx. Okay, well, if we look at this formula here, which is simply saying take the derivative of y with respect to x, and that gives us all of this. Down here we're saying we'll take the derivative of dy dx with respect to x. So all we have to do is replace y in this formula with dy dx. So it's like saying the derivative with respect to t of dy dx, all divided by dx dt. So in summary, we have dy dx, which is dy dt over dx dt, and we have the second derivative of y with respect to x, which is the derivative with respect to t of dy dx, and that's divided by dx dt. And these are both functions of t. All right, so yeah, let's go and do some examples now. Okay, so here we're going to find both the first derivative and the second derivative of y with respect to x. And we're also asked to find the x values for which the curve is concave upward. And here's the set of parametric equations. So yeah, this is the infinite nose curve, and we'll take a look at that at the end. So we'll start by finding the derivatives. Okay, well, the derivative of y with respect to x is, of course, the derivative of y with respect to t divided by the derivative of x with respect to t. So we're going to need both of those. Okay, so dx dt is derivative of t squared plus 1, so that's 2t. And dy dt is the derivative of e to the t minus 1, so that's just e to the t. So returning to our dy dx, which is what we're really after, we can now put the pieces in. So dy dt in the numerator, that's e to the t, divided by dx dt in the denominator, that's 2t. So very good, we found our dy dx. Next, we need to find the second derivative of y with respect to x. Okay, so let's recall that formula. That is the derivative with respect to t of dy dx, okay, which we just found, and that's again divided by dx dt. So derivative with respect to t of dy dx. So that's e to the t over 2t. And over dx dt, which we know is 2t. Okay, so we just have to actually work out this derivative in the numerator, which itself requires the quotient rule, so we're going to have kind of a fractional mess to deal with, but at least we know how to deal with that. So let's go and do that. So using the quotient rule, we have the derivative of the numerator, which is e to the t, times the denominator, minus the numerator, times the derivative of the denominator, which is 2, over the denominator squared. And this itself is all over 2t. Okay, so we can clean this up a little bit by factoring 2e to the t out of the numerator. Here we have 2e to the t times t minus 1, and this is all over 2t quantity cubed. Well, one of the 2's will cancel, so we're actually going to get just e to the t times t minus 1 over 4t cubed. Okay, so we found both the first and the second derivative. Let's just write them down one more time. The first derivative was e to the t over 2t, and the second derivative is this thing. Okay, so the second part of this question asked, for which values of t is the curve concave upward? So the curve is concave upward when the second derivative, of course, is positive. So we just need to solve that inequality. Okay, well that's this inequality, of course. Okay, so to solve an inequality like this, the best way to do that is to kind of draw a real number line. And first we're going to locate all the points where this expression is equal to 0 or is undefined. We can see by this factor here that this expression is equal to 0 when t is equal to 1. And we can see by the denominator that this expression is undefined when t is equal to 0. This gives us 3 distinct intervals that we need to check to see if the inequality holds over that interval. So we're just going to test different values. So we'd test something in this interval, like t is equal to negative whatever, t is equal to negative 1 billion, it doesn't matter. If we plug it in here, we can see e to that will be positive, negative 1 billion will be negative, negative 1 billion cubed is negative, so negative over negative is positive. So the inequality is satisfied over that interval. Now if we let t be something between 0 and 1, like say 1/2, we plug that in, we're going to get e to the 1/2, which is positive, 1/2 minus 1, which is negative, over 1/2 cubed, etc. That's all positive, so we have negative altogether. So this is not included. And now pick something to the right of 1, like 2 or 3 or 1 billion. And again, we have positive, and 1 billion minus 1 is 1 billion. That's positive over positive, so everything's positive. So these two intervals make the inequality true, which means that the curve is concave upward for those t values. So that's the interval negative infinity to 0 and the interval 1 to infinity. So let's take a look at this nifty curve on Desmos. All right, so here we have the sketch of this particular parametric curve. And you can see that this part of it here is concave up. And this little part right here looks to be concave down. And then the rest of it up here is concave up. So let's actually see if the transitions occur where we want them to. And we think the transition occurs at t equals 0 and t equal 1. So as long as t is less than 0, and you can see the little dot here representing the particular point we're looking at. And on Desmos, we have to call it A in order to make Desmos happy. As long as that value is less than 0, we are looking at a concave up area. But as soon as we set that equal to 0, which is right here, the concavity changes from concave up to a segment where it's concave down. And it'll be concave down until A here, which is really t, gets to 1. So it's concave down, and then look at A increasing, and now A is at 1, and that's another inflection point, and everything beyond that is going to be concave up. So here we are with values between 1 and infinity, and it's concave up there. So our analysis agrees, of course, with the nature of the curve. All right, so here we need to find the equation of a tangent line to this curve that's defined using parametric equations at the point corresponding to a t-value of 0. Okay, so let's recall the equation of a straight line. So to answer this question, we are going to need these three pieces, x0 and y0, which are, of course, the point given by t equals 0. That's easy to find. And m, which is, of course, given by dy dx at the point t equals 0. So this is just going to be y of 0, and this is going to be x of 0. We'll calculate those in a minute. And here, this is dy dx at the point t equal to 0. All right, so yeah, let's quickly get those pieces. So x0 being x of 0 is e to the 0 sine pi times 0, which is 0. And y0 is y of 0, which is e to the 2 times 0, which is 1. So therefore, our equation is y minus 1 is equal to m times x minus 0, or y equal mx plus 1. So we just need to find m. Okay, well, dy dx is, of course, equal to dy dt divided by dx dt. So now we need those two pieces. All right, well, dx dt is the derivative with respect to t of the x function. So that's e to the t sine of pi t. All right, we'll need the product rule here, derivative of e to the t times sine of pi t plus e to the t times the derivative of sine of pi t. And I'm not sure if it'll be helpful, but let's factor e to the t out because it looks like it wants to do that. Okay, so there's our dx dt, which will ultimately be the denominator of our dy dx. Of course, we also need dy dt, which is the derivative with respect to t of our y function. This one seems a little more straightforward. There we are. So returning to dy dx, we have this guy worked out, and we have this guy worked out, so let's put them together. Oh, well, I'm glad we factored that e to the t after all, because a little bit of cancellation occurs. And and we get 2e to the t over just the trigonometric part. Okay, so remember we wanted the derivative at 0. That's what m is, right? So at t equal to 0, we have our m value, which is going to be 2 times e to the 0 over sine of pi times 0 plus pi cosine of pi times 0. So that would be 2 over pi. Okay, so therefore the equation of the tangent line, which we left off as y equals mx plus 1, is y equals 2 over pi x plus 1. So that is the equation that's tangent to our curve at the moment that t is equal to 0. Let's see what this looks like on Desmos. Okay, so here's the curve on Desmos. It's actually pretty neat. If you keep zooming in here toward the origin, it just kind of keeps lapping inward and inward on itself and continues to do that forever. So fortunately, that's not the part we're doing our intensive analysis on. We are interested in the moment when t is equal to 0. So that actually corresponds to the coordinates 0, 1. So that is this point right here on our curve. And you can certainly imagine the tangent line going right through that. Let's see if we got the right answer. So we'll write this y equals 2 over pi x plus 1. I'd say that's pretty good. Okay, so here we have a set of parametric equations, and we are asked to find the points on the curve where the tangent is either horizontal or vertical. Now, you may recognize this particular curve because we sketched it in our last lecture, and we got the lemniscate, which means visually we can sort of answer the question. Obviously, these are the points where the tangent is horizontal, and these are the points where the tangent is vertical. So what exactly are the coordinates of these points? Well, we're going to conclusively establish what the coordinates are using calculus. All right. So obviously we're going to need a derivative, dy dx. That's going to tell us everything. So we know the tangent's horizontal when the derivative evaluates to 0. And the tangent will be vertical when the derivative is undefined. So yeah, let's find the derivative. Okay, so of course we know that the derivative of y with respect to x is dy dt divided by dx dt. So yeah, we just need both of those things. So dx dt is the derivative of x, which is cosine of t, and that's negative sine of t, of course. And dy dt is the derivative of the y function, which was sine of 2t, and that is 2 times cosine of 2t. So therefore, dy dx, which of course is this, will be dy dt, so that's 2 cosine of 2t divided by dx dt, which is negative sine of t. All we're interested in here is figuring out what t values are where this derivative is equal to 0 and what the t values are where this derivative is undefined. Okay, so let's solve dy dx equals 0. All right, multiplying both sides by sine of t, we get. So to answer this question, we're going to ask the question, what are the angles whose cosine value is equal to 0? And we know that that's pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So like odd multiples of pi over 2, right? So we can see this means 2t is pi over 2 plus some multiple of pi. Or dividing everything by 2 to get t, we're going to see this as pi over 4 plus multiples of pi over 2. Okay, so visually, where are these numbers? Well, here's pi over 4. And then here's another pi over 2 plus that. And another pi over 2 plus that. And another pi over 2 plus that. So it's all of the like pi over 4s, right, that satisfy this particular equation. Now, the original question asked to find the points on the curve, so meaning specifically the xy pairs. So we have the t values here, but we actually need to find the corresponding x and y values. Okay, well, recall that x is equal to cosine of t. So cosine of pi over 4, 3 pi over 4, 5 pi over 4, etc., those are just plus or minus rad 2 over 2. And our y, which is sine of 2t, so doubling these numbers, that's like, what is sine of pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc.? Those are like plus or minus 1. So looking at our graph, you can see that we've found the locations where the tangent line is horizontal, and that would be at x plus or minus rad 2 over 2 and y plus or minus 1. Now let's see where the tangent line is vertical, and we can expect that it's at these 2 points right here, which is positive 1, 0 and negative 1, 0. But let's figure it out analytically. So here's dy dx, and we can say that it's undefined when the denominator, sine of t, is equal to 0. So that's just the equation that we have to solve. Okay, well, we know that this occurs at multiples of pi. So corresponding xy values, well, x is cosine of t. So when t is a multiple of pi, then x is just plus or minus 1. And y is equal to, of course, sine of 2t. And again, when t is a multiple of pi, sine of 2 times multiple of pi, that's still very, very 0. So we'll get y equals 0. Okay, so we can put everything together in a nice conclusion. Okay, very good. All right, well, what about arc length? This is actually very straightforward to find in parametric curves. So let's quickly recover the formula that we're going to need. Let's imagine we have a curve and it's just minding its own curvely business. And we are interested in finding an arc length. So let's just approximate it by adding up the straight lines between 2 points on the curve. Now, we're imagining that these points are very, very close to each other, infinitesimally close. So we're going to call this horizontal distance dx and this vertical distance dy. And using the Pythagorean theorem, this particular differential length along the curve is given by this formula right here. So to find the arc length, all we have to do is add up all of these things. So we'll say that the arc length L is the sum from A to B of these guys. Okay, but if we're not careful, we're going to end up just factoring dx out like we did back in chapter 8 and getting the actual arc length formula in terms of a Cartesian equation, which is not what we want. So we want this in terms of parametric equations. So no problem. We'll just put in what we want. We want this to be with respect to t. So we'll just put in a dt. But we have to, of course, divide by dt. So taking the numerator dt and moving it to the far right, which is where we kind of want d whatevers to be, and taking the denominator dt and moving it into the radical where it will become squared, we get the following. And there it is. This is our arc length formula. So the length along the curve from t equals a to t equals b is just this particular formula with these derivatives, dx dt and dy dt, put in where they belong here. So yeah, let's go and do an example. All right, so here we're interested in finding the arc length of the curve generated by this set of parametric equations. So before we go and do the calculus, let's get a quick visualization of this using Desmos. Okay, so here's the thing on Desmos. We've actually sketched it from t equals 0 to 2 pi, just to give a little more graphical context. But what we really want is just from 0 to pi. So let's go put that in. And you can see it's just the top half of this snowman thing. So we want the exact length of that curve. And really what we're asking is if you had a string that was this thing and you pulled it straight, what would be the length of that string? So as an interesting visual exercise, pause the video and just try to guess. What do you think the length of this purple curve is? We have all these dimensions on the page that can help you kind of give a sense for how long it might be. And now that you've made your guess, let's go and work it out. Okay, so obviously we're going to use the arc length formula, which for parametric curves looks like this. So we're going to need these pieces. Okay, so dx dt is the derivative of what x was. And dy dt is the derivative of what y was. Okay, so what do we have here? We are integrating from 0 to pi, because those are the bounds on t. So what goes in here? Well, dx dt squared. So we found dx dt, which was this. And we're adding to that dy dt squared. So that would be the square of this thing. Okay, so now all we have to do is just pull out our super awesome integration skills and we're home free. All right, we're going to have a FOIL fest here. So the square of this term is 9 sine squared t. And then we're multiplying these two together and doubling. So that's going to be minus 18 sine t sine 3t. And then we are squaring this term. Okay, and we're going to FOIL out this one as well. So we're going to square 3 cosine t. That'll give us 9 cosine squared t. And multiply these together, doubling, we'll get negative 18 cosine t times cosine of 3t. And we aren't going to quite fit everything, but let's just pretend like this big old fat radical continues. And we'll square this term. So we're going to get plus 9 cosine squared of 3t. And that's the end of the radical, and then dt. Okay, well this is surely a mess, but let's see if anything nice is going to happen. So 9 sine squared plus 9 cosine squared, that's actually just going to be 9. Okay, so we've handled that term and that term. 9 sine squared 3t plus 9 cosine squared 3t, that's also going to be 9. So we've handled those terms. And we can factor negative 18 out of these two remaining terms. And this is starting to look a little bit more palatable. In fact, what is this thing here? we can see that this is actually cosine of 3t minus t. So what are we getting here? 9 plus 9 is 18, so we get 18 minus 18 cosine of 2t. Okay.
Now this is pod racing.
No, it's not. We're just working out an integral. So we can even factor the 18 out of the radical. It would come out as square root of 18, which is, of course, 3 rad 2. And we have radical 1 minus cosine of 2t. But recall that sine squared of t is 1/2 of 1 minus cosine of 2t. And therefore, 2 sine squared t is equal to 1 minus cosine 2t. Well, that's very nice. So we have here another rad 2, and then the square root of sine squared t. Okay, but between 0 and pi, which is the first and second quadrant, sine is positive, so the square root of sine squared is just sine. Also, rad 2 times rad 2 is 2, so 3 times 2 is 6. So we have 6 sine of t dt. Okay, this integral doesn't look too bad. No. So 6 sine of t integrates to negative 6 cosine of t. And we'll plug pi in at 0, so we get negative 6 cosine of pi minus negative 6 cosine of 0. Cosine of pi is negative 1, so this becomes positive 6. Cosine of 0 is positive 1, so we get plus 6. And the final answer is exactly a length of 12. So if you guessed about 12, then nice job. You're right.